is secant squared x minus tangent squared x plus cotangent squared x. We're going to do this 3 ways. So I want you guys to think about how you would solve this. Go ahead and solve this using the following information. If you know that tangent squared x plus 1 is equal to secant squared x, that's one of our key Pythagorean identities. And you know the other one as well, that 1 plus cotangent squared x is equal to cosecant squared x. Use those 2 pieces of information to see if you can transform this down to 1 trigonometric ratio. Or what can we do right there? Okay, good. So, and those are 2. I guess there's 2 ways of visually thinking about it or writing it by hand. You can either do exactly what she said and say, okay, that right there, that's secant squared x, and that secant squared x can be or are the same thing, right? So replace this one over here on the left with tangent squared x plus 1, and then you got this minus tangent squared x still, plus then cotangent squared x, okay? And Abby said that and that are opposites, leaving you just the 1, right? All right, it's a great way of doing it. That's not that's cotangent squared. So it leaves you with that, okay? Some of you might be kind of accustomed, this is kind of the way that I've been doing it, to come to the side and just rewrite this as 1 equals secant squared x minus tangent squared x, and that there is exactly that right there, right? And you can make that substitution to get 1. But either way you think about it, it's the exact same approach, just kind of maybe looking at it from a different perspective. Either way you do it, okay? But what is now 1 plus cotangent squared x? Cosecant squared, okay? Would you agree that was a fairly simple simplification process, okay? But it's only simple if you know these 2 things, right? And hopefully we do. And not even just knowing them, it's being able to recognize their different formats, being able to recognize when they exist inside your problem, that kind of thing, which takes some practice, that takes some skill. Let's do this a second way. And maybe we develop then, for those of us that aren't recognizing these identities, aren't taking time to learn them, hopefully the second approach maybe proves to you their necessity or their efficiency. So let's take this and let's rewrite it as, just gotta get rid of this stuff here. Can we rewrite this as 1 divided by cosine squared x minus sine squared x over cosine squared x plus cosine squared x over sine squared x? Can we do that? Okay. Now, when we're doing that, my eraser right here. When we do that, there's the same exact substitutions are going to occur. You just aren't going to see them in their current format. Does that make sense? Or the format that we are accustomed to. For instance, when we said that 1 was equal to, what was it, secant squared x minus tangent squared x, okay? Well, now, because we're dealing with sine and cosine, this is going to be 1 over cosine squared x minus cosine squared, or sorry, sine squared x over cosine squared x. So you still see that right here, right? Okay? But most people aren't going to remember these IDs, these Pythagorean identities, in their sine and cosine formats. So what I want you to understand is that those same substitutions are occurring. We're just kind of dealing with it in an alternative way. Okay? So what I think is useful when we have this, we're not going to, when we change things to sine and cosine, you don't rely so much on your identities, you rely on your algebra skills. So what you've learned in Algebra 1, Algebra 2, Algebra 3, in regards to just how we simplify, evaluate either expressions or solve equations, okay? So if I'm going to take a bunch of fractions and start adding them together, what do I need? Common denominator, okay? And I agree with you 100%, but let's think about this. Let's say I had like, I don't know if I said this last week, I did an example like this, like 1/3 minus maybe 2/3 plus 1/5. The LCD there is going to be 15 amongst all of those, right? Okay. But can't I do that addition or subtraction first? Yeah, I can associate the like terms, the like denominators, do that addition, and then get, okay, so 1/3 minus 2/3 would be negative 1/3, right? And then plus 1/5. That might make things a little bit easier. Now, I still have to come up with the LCD of 15 here when I go through and add these together, right? That may or may not occur when I deal with these. Let's just see. We recognize that those two have an LCD, right? Or already have a common denominator. So let's rewrite this as 1 minus sine squared x over cosine squared x. I think once we do this a third way, you're going to appreciate this process here of being able to do this, okay? Recognizing that I do have, of the three ratios, 2 that I can add together pretty quickly. Now, what is 1 minus sine squared? What's that the same as? Yeah, that's cosine squared, right? Okay. So I'm going to rewrite this as cosine squared x over cosine squared x plus then cosine squared x over sine squared x. Now, what is this fraction right here going to turn into? 1. So I have now 1 plus cosine squared x over sine squared x. And now we're at the same stage we were at when I had negative 1/3. I think it was plus 1/5 or something like that. I still have to use that 15 as a common denominator here, right? So I combine these two. I still have 1. Now I'm adding to another ratio. So I still need another denominator. I need another LCD. What's that other LCD going to be? Sine squared. So I'm going to take this 1 and rewrite it as sine squared x over sine squared x. Now, what's the benefit of doing that? It's now, with that denominator of sine squared x, I can rewrite the top as sine squared x plus cosine squared x, right? And what is sine squared x plus cosine squared x the same as? 1. So you get 1 over sine squared x, which what's that the same as? Cosecant. Is that the same answer that we got using method 1? Would you now have an appreciation over method 1? Yeah, okay. Knowing those identities got us that answer so much faster. Yes, yes. So that's another thing. So, and those are really good things to be able to see as you're doing these problems. Alternative places to have stopped. Okay. So we're looking there, and Abby's saying if we look at stop there and say, okay, 1 plus cosine squared over sine squared, we make that substitution. That's 1 plus cotangent squared x. And what's 1 plus cotangent squared x the same as? Cosecant. So yes, that's 100% perfectly fine to do it that way. And that's the nice thing about these, but it's also, and it's algebra in general, it's the thing that stinks about them as well, is because Is there one cut dry way of doing them? No. Okay. Some of them there are. Some of them this is the only way you can do it. But others, you see this one, we've got now that might be a third way of doing it. Okay. And then that opens the door. So as a teacher, how do I show all the possible ways? Okay. I think it's a good idea, a good approach to take one and recognize that there are varying techniques, varying procedures, and if you keep that in mind, hopefully that helps some of us. Let's do this a third way. Let's do it over here. This third way is going to, I think, help you realize how beneficial doing that was. Okay, combining those two initially. Okay, because if we don't combine those two initially, all right, so I'm going to start off with just 1 over cosine squared x. And then minus sine squared x over cosine squared x. If I want to add three fractions together, I need the common denominator, right? Okay. Now, we've talked in the past that if I had, I'm just going back to numbers, 1/2 plus 2/3 plus, 1/6. Okay. What's the LCD amongst those three? 6. That's the least common denominator, right? Meaning I can make every one of those denominators turn into 6 in multiplication. But what is another common denominator? 12. Turn them all into 12, right? Can turn them all into 18. Can turn them all into 36. Yes. Okay. But when I do that, when I turn them all into 36, that's going to make my numerator, that one numerator, 18. It's going to make the other numerator, the 2 there, it's going to make that, what, 24? It's going to make the other one 6. So my numerators become bigger, right? Now draw a comparison to what would happen up here if I were to do something like that, okay? Our common denominator here is going to be cosine squared x, sine squared x, right? Okay? But if I wanted to make it cosine of the fourth x, sine squared x, that is perfectly fine. Make sense? Based off of what we know about our algebra. However, that now is because we're going to multiply basically our top by cosine squared x in that first ratio, or sorry, cosine squared x, sine squared x in that first ratio. We multiply by cosine squared, sine squared in the second one. We multiply by cosine squared in the third one. Sorry, cosine of the fourth in the third one. If we were to do that, our numerators become very, very complex trigonometric ratios that are going to be really, really hard to simplify. Does that make sense? So when you are multiplying, adding, subtracting fractions in trigonometry like this, with expressions like this, you're going to want to use the LCD. Does that make sense to everybody? A similar thing happened when we were talking about like rational equations in algebra. When we had a denominator that the LCD is preferred, because if I multiply by something greater than the LCD, then I might develop like a numerator that is x to the third or x to the fourth, and those are harder to factor than maybe x squared if I were to use the LCD. So you want to come up with LCDs here and not just general common denominators. Okay. So that LCD, cosine squared x, sine squared x. So I just go through and kind of develop that structure for these three ratios. It helps me organize. It helps me remind myself of what I need to multiply each numerator by to get that denominator. So these two ratios are ultimately the same one. Okay. So what did I need to multiply this cosine squared by to get this sine squared? So that's what I'm going to multiply the top by, right? And think about what we just did and why this is legal to do, guys. I just multiplied the bottom by sine squared, and I multiplied the top by sine squared. Well, what's sine squared divided by sine squared? 1. Okay? That's why we can use LCDs, or just common denominators in general, because when we transform the numerator as well, we're ultimately just multiplying by 1, which does not change the quantity that is existing here. Okay? Multiply this one by sine squared. So sine squared times sine squared is sine of the 4th. That's kind of ugly. It's not too bad, but if we didn't use the LCD, this thing could be even greater than 4. It could have another kind of trig ratio attached to it, and that it's going to be very hard for the next step that we're going to go through. So it is nice that we're using the LCD again. And then I need to multiply this one by. All right, so we get that new expression. Now that we have the common denominator, now I'm going to go through and just actually do the algebra. I'm going to condense this to cosine squared x, sine squared x on the bottom, but the numerator becomes sine squared x minus sine to the 4th x plus cosine to the 4th x. Okay? Now, some of you might be looking at that and say, that numerator looks similar to a question that we did get, I think on Friday out of the homework. I think it was like sine of the 4th minus cosine of the 4th. Okay? And we could use a difference of perfect squares. Can I do that here? Can I group? Can I maybe group these two here like this and say that those are a difference of perfect squares? No. Okay. Now, and I don't know. I haven't done it this way, but and you know as well that the commutative property exists with addition, right? Could you maybe flip-flop some things around? Could you rewrite this as cosine of the 4th x minus sine of the 4th x? Okay, so that's an option. I'm kind of interested maybe when we're done here, because I want to go a different route, see if that works. But I want to give you kind of varying ways of doing problems. So I don't want to use the same technique that we've already used maybe earlier. But if I look at those two, what do you recognize about those two? Do they have a GCF in them? So can I rewrite those two as sine squared x and then 1 minus sine squared x? And then over cosine squared x. Sine squared x, is that something we can do? Now what does this 1 minus sine squared become? Cosine. So now we got sine squared x cosine squared x plus cosine to the 4th x all over cosine squared x sine squared x. Erase some of this. Can we look at these two terms now? Because this is sine squared x cosine squared x is one term. Cosine of the 4th is another term. What is the GCF in those two? Cosine squared. Let's factor that out. So factor cosine squared out. Now I get sine squared x plus cosine squared x all over what? Cosine squared x times sine squared x. Correct? What does this turn into? 1. What happens with these two things? Cancel. So I get 1 up top, and I get sine squared x on the bottom, right? What's that equal to? Cosecant squared. Okay? Same approach, right? Or same answer, maybe a different approach. Okay? A lot more substitute, or I don't know, maybe substitute. There are more triggers. We use some identities there. 1 minus sine squared x. We use sine squared x plus cosine squared x. There are more substitutions there. There's a lot more kind of heavy lifting in regards to our algebra, right? but still gets us to the answer. Okay. I just want to see something real quick. If we went back and messed around with this again, and like I said, rewrite this as I'm gonna just rewrite it as cosine to the fourth x minus sine to the fourth x plus sine squared x. Now that kind of generates a question that we saw maybe on Friday, where those two things can be rewritten as cosine squared x minus sine squared x. They're a difference of perfect squares. Cosine squared x plus sine squared x, and then plus sine squared x. So this here, that one turns into 1, right? So now I have cosine squared x minus sine squared x plus sine squared x. Those two things are additive inverses, right? So they go away. So now I have cosine squared x. Now I haven't been writing the denominator, but the denominator is still cosine squared x sine squared x. Now what happens with the cosine squared x's? Cancel, and it leaves me with 1 over sine squared x, which is the same thing as cosecant squared x again, right? So the idea here, guys, is that there are a lot of different ways of doing it, okay? And when we go over one in class for homework, you say, is it, those questions you have, is it okay if we've done it this way? Those are great questions. Those are some of the best questions you guys ask all year, because you're starting to see the different algebra that can present itself in the different ways you can attack it, okay? Now, I want to kind of draw a comparison with that identity, because we just said that was equal to secant squared x minus, if you go back to what we started with, all the way about 25 minutes ago, we started with that. And we just figured out that that is the exact same thing as cosecant squared x, right? Okay. What you're going to be asked today with some of our questions is it's extremely similar to what we've been doing, just kind of maybe a different format, maybe the way you organize your information, your work might be a little bit different, but instead of them writing the directions where they said simplify down to one single trig ratio, they might say prove the following identity. Okay, prove the following identity. Meaning that they want you to show algebraically that that left-hand side is exactly the same as the right-hand side. Okay? Or vice versa, show that the right-hand side is the left-hand side. Okay? When we do these, when we prove identities, and again, there's going to be multiple ways you can do this. Essentially what we're going to try to do is go through simplification of one or both sides. Okay? And the hope is that as we kind of break that left-hand side down, eventually a term will pop up that is cosecant squared x. And we recognize that is exactly the same as the right, so we stop and we say, yes, we have now shown that the left-hand side can be transformed into the right-hand side. Does that make sense? Okay. Sometimes we'll work on the left-hand side, and we'll be working, and we get to a roadblock. We get stuck. We don't know what to do. Well, then we can pick up with the right-hand side and continue to work with the right-hand side and transform it, and then hopefully maybe somewhere on the right-hand side we see work that matches up with something on the left-hand side. Okay? To kind of give you some examples of what I'm talking about here, before I give you examples, I'll give you some maybe guidelines to help you prove trigonometric identities. Now, these are just guidelines. And guidelines can be broken. They're not written in stone. Don't always follow them to a T. But for the most part, I think the ones that you guys are going to see right now, these are probably going to be sufficient. Okay. Basically, what it says is start with one side. Okay. Pick one side of the equation, write it down. So your goal is to transform it into the other side. It is usually easier to start with a more complicated side. Okay? If you start with the simpler looking side, you're going to have to make substitutions that are kind of backwards, or you'd be thinking about them backwards. So maybe my easier side is cosecant squared. Well, then I have to transform that to maybe 1 plus cotangent squared. So I have to expand it, make it look more complicated. That's just more difficult. Okay? So we're going to start with the simpler looking side. And that's totally kind of like a personal opinion on which side is more complicated. I think when I see fractions, that's going to kind of dominate and say that side's more complicated. Okay? The more ratios that I see, the more terms that I see, starts to indicate that side's maybe a little bit more difficult. And then step 2 is use known identities. Okay, use algebra and the identities you know to change the side you started with. Now, I don't think maybe a fair statement when it says use algebra, because what that is incorporating, it says use algebra 1, algebra 2, algebra 3. Use 3 years of math to start simplifying these things. Okay, and that is the idea of bringing fractional expressions to a common denominator, factoring, using fundamental identities, all those things that we've been kind of working on for the last several years. Okay, and you start to see that this is maybe like a culmination of algebra 1, 2, and 3 all together in one topic. Okay, and the last thing, if you get stuck, this is kind of the thing that we turn to. In the past, guys, I've had people turn to this right away. This is the first thing that everybody does. Okay, nothing wrong with it. It's going to make you rely on your algebra a little bit more, but change everything in terms of sine and cosine. If you think about it, those are the exact same procedure that we kind of dealt with when we were doing any kind of simplifying, except for that added component that now we're going to start with the complicated stuff. Okay. If you work with the side, if you choose a side and you keep working with it, and you're not seeing it show up as the right-hand side or the other side, don't erase it. Don't stop. Just pick up with the other side and start doing the same thing with the other side, and then hopefully, as you make kind of like 2 columns of work, somewhere in the first column you'll have an expression that matches up to one of your expressions in the right-hand column, and that would be the link to show the cosine. Okay. Yeah, they're going to be proofs. So they're going to be true. We just have to then verify. Okay. Good question. They usually ask you to kind of verify it algebraically, which obviously that's what I'm really interested in. But we understand there's a graphical approach to these. So if we use the graphical approach, I'll just graph these from last period. That is the left-hand side of what we're going to graph: cosine x times secant x minus cosecant, cosine x. And they're showing that is equal to sine squared x. And if we graph them, we do see that the red one and the blue one are on top of each other. So they are the same. Okay, so we're going to try to prove and verify that they're the same algebraically. One thing I want to talk about, I had this issue with someone earlier, I guess not earlier, but late last week. They were trying to use their TI-83 and 84 to graph things, which is great. They graph something, they put something in y1. Okay, so that's how I got to type in sine squared. And I graph it, and when I start graphing it, you see that it's thinking it's working, it's graphing, and that's not sine squared. That's not what Desmos gave us, right? And the person that actually came to me, they knew that you'd be getting a periodic curve, but it was just graphing like a horizontal line. Okay, and that happens from time to time. But basically, what's going on here, I guess my best answer to you of what your calculator is doing is remember your x-axis is a distance, your y-axis is a distance. Okay, and when I put in degree mode, degrees are not distances, right? Okay, so your calculator, I don't think, is transforming your degrees into radian measurements as distances. Does that make sense? So the only thing that you got to do whenever you're graphing any one of your trig ratios on your 83 or 84, you got to make sure that you're in radian mode, and then when you graph it, there's no issues. Okay. Now on your tests, I'll let you use. You guys want to bring in your computers and use Desmos? I'll let you do that. I don't care. If you want to use TA3s, A4s, that's definitely an option. But you know, we've been using Desmos a lot in class. I've been telling you to use it, so that is something to allow. Now, if I look at this one, so we're going to do this example. It says consider the equation cosine theta times the quantity secant theta minus cosine theta is equal to sine squared theta. If I look at that, obviously we've got, and this is what we call, just the notation here, guys, we're going to call this LHS, and this is RHS. You see that a lot when we're trying to prove algebraic equations or identities. What do you think LHS stands for? Left-hand side, right-hand side, okay? So which side do you think is the more complicated side? Left-hand side. So usually the notation is that we take the left-hand side, which is equal to cosine theta secant theta minus cosine theta. And now, ultimately, guys, I have now taken my equation and I'm concentrating on one side. So now I've been basically going back to what we've been doing the last 2 or 3 days. Let's look at that and see if we simplify that. Okay. Now there's no powers of 2 here, so there's no real nice Pythagorean identities to incorporate, but there is a secant in there, and you may be a person that says, well, let's change that secant to 1 over cosine. That's perfectly fine. You can do that. But I recognize that there's some algebra here. You know, if I had like x and x plus 3, what's that algebra tell me to do? Distribute, correct? Isn't that what this algebra tells me to do? And here's the reason why I would not change this to a 1 over cosine, because I want to save myself a little bit of writing. When I multiply those together, I get cosine times secant, right? And even if you want, you can write that. You don't have to, because what is cosine times secant? What are those two things to one another? They're reciprocals. And what is the product of 2 reciprocals? That's 1. That's the definition of reciprocals, right? So I get 1 minus, come on, there we go. 1 minus cosine squared theta. What's 1 minus cosine squared theta the same as? Sine squared theta, which is equal to your right-hand side. So through, and the way we kind of wrote this, through our transitive property, the left-hand side is what we started with. It was equal to this, which is equal to that, which is equal to that, which is equal to that, which is equal to your right-hand side. Have we shown that your left-hand side is your right-hand side? Yeah, okay. So we've proven this. A lot of times when they, when you prove something, a lot of times they put like to show that we've come to a conclusion, they put like a little box and they shade it in. I think sometimes they write like QED or something like that. Okay. Which I think is like Latin for something to do with I've proven what I've been asked to prove, something like that. Those are just little notation. If you're ever reading like the back of a book, sometimes you see that notation. That's why I wanted to use the LHS and the RHS, because in the back of a book, that's kind of the terminology that the author will use, and you'll see occasionally these little boxes, and just want to show you what that stuff means. All right, so let's do that. Hopefully you realize that, you know, I could have started here, but it kind of gets difficult and saying, okay, well, sine squared, that's 1 minus cosine squared. And now cosine squared, well, that's, you know, 1 minus maybe 1 over secant squared. And it's really hard to start working my way backwards to get this, right? Does that kind of make sense? Not even sure. Maybe I would go and rewrite this as secant squared over secant squared minus secant squared, 1 over secant squared. It's just not the easiest approach to do. Okay. Now, there are times where you're really not wrong with choosing one side over the other. I'm going, I mean, I told you at the beginning, when I see fractions, I think that's the side that's going to be hard, for the most part. Okay. So I'm going to choose the left-hand side here and start with that. And maybe if we have time, I don't think we will, we could look at the right-hand side. Maybe we'll look at the right-hand side tomorrow and approach this question that way. If I start with the left-hand side here, another reason I want to show you this left-hand side or work with this because it brings in a piece of algebra that we've used in the past. We just haven't used it lately. We haven't used it yet in a trigonometric problem or evaluation simplification problem. And that process involves us kind of looking at this thing and realizing there are really no nice substitutions in that left-hand side. Okay? So we actually have to do something to this to allow a substitution to kind of generate itself. Okay? And the way we're going to do that is we're going to multiply by a number. Okay? Now realize what we're doing here. I just grabbed the left-hand side of the equation, right? So I'm not trying to balance an equation right now. Okay? I'm looking at an expression. Okay? So if I'm looking at an expression, can I take, let's say, you know, for instance, if I had 2/3, 2/3 in an expression, right? Okay. Can I multiply 2/3 by anything that I want to and still get 2/3? Can I multiply that by 2 and still have 2/3? 2/3 times 2 is still 2/3. Now think about my question. Can I take any expression and multiply it by something and not change the value? No. Okay? That's the whole thing, multiplication, right? It doubles it, triples it, whatever. Okay? I can't add anything to that. I can't do any operation to just an expression because it's going to change its value. Okay? Now, if I was working with an equation, yes, I could multiply this side by anything that I want to, as long as I multiply that side by the same thing, right? So that's the balancing idea. But if I'm just looking at this left-hand side here, I cannot just multiply by anything I want to because it's going to change, it's going to unbalance ultimately the equation, right? Okay, so I'm not going to do the same thing to the right-hand side. But there is one number I can multiply 2/3 by so that doesn't change it, so that I keep 2/3. What would that number be? 1. Your multiplicative identity, right? Okay, and it can show up. Can I multiply? Now, 1 over 1, that'd be kind of boring because it's just going to give me 2/3, right? But can I do this? Does it still give me 2/3? Yeah. Just written as 4 6s right now, right? Okay. I can multiply by any value of 1, any form of 1 that I want to. So we're going to do the same thing over here. And that value of 1, or that form of 1 that I'm going to use is told to me right here. Because that looks eerily similar to that, doesn't it? Except for the powers are different, correct? Okay. Now, the reason maybe I'd want to go to this, because isn't 1 minus sine squared u? Isn't that the same thing as cosine squared u? That makes sense, everybody? So I could have a really nice substitution here if this thing here on the bottom was 1 minus sine squared u. Anybody know how to get to that? Let's say I had x plus 2, but I wanted to get that in the format of x squared minus 4. How could I do that? Multiply by x minus 2. What were those two things to one another? Conjugates, right? Okay. So, what would be the conjugate of 1 minus sine u? 1 plus sine u. Now, is that still multiplying by 1? Yeah, it's just a convenient version of 1. Okay? when I multiply the numerator, so the numerator says that I've got a monomial times a binomial, so I've got to distribute. So I get cosine u plus cosine u sine u. And on the bottom, I get 1 minus sine squared u. Well, what's that bottom turn into then? Cosine squared u. That's this substitution right here. Now I got cosine u plus cosine u sine u. Okay, now you can break this up as many kind of intermediate steps as you want to, but do we realize that there's a cosine u in this numerator as a GCF? Can I take that cosine u out? I guess I'll do it in steps. Cosine, you take the cosine u out, and that would give you 1 plus sine u, right? Over cosine squared u. What's going to happen with these cosine u's? That one's going to cancel, right? Now this one's going to cancel as well, but there's 2 down here, right? It's cosine u times cosine u. So really only one of them cancels out. So now I'm left with still 1 plus sine u up top and cosine u on the bottom. Okay? Now I'm going to draw a comparison to what we could do algebraically. If I had like 2 plus 3 over 5, that probably came, when I write something like this, probably before that it looked like this. 2 over 5 plus 3 over 5, right? And with the equations, we know we can either move that way or move that way, right? So can I separate this one as well? Can I write this as 1 over cosine u plus sine u over cosine u? Now what's 1 over cosine u? Secant. And what's sine over cosine? And what is that? Your right-hand side. Okay. Something else to kind of think about if you're using a back of a book, or maybe you're looking at maybe WebAssign. I don't know how they generate their solutions when you're wrong and they show you what the steps were. They might not write that. Okay. They might go straight from this and write equals RHS. Okay. Because it does equal the right-hand side, right? Okay. So now that's not the only approach. Maybe tomorrow we'll start off with the right-hand side and see if that comes out to the left-hand side. Okay. The next example, I think we're probably looking at that. Maybe we have to work on both sides. I'm not sure. Okay. It does say work on both sides. So we'll do that. I'll open assignment with the next couple hours, I guess. It's not due tomorrow. I won't be due for a while. That's kind of the thing we're going to work on for the next day or so is this, and then introduce, maybe towards the end of the period tomorrow, introduce a few more identities. Okay. And when I say introduce them, I show you how they're derived. Okay. Go through their creation, and then once we create them, we can use them all the time. Okay. But yeah, so I'm going to update your grades. I finalized your grades for the last 9 weeks. I got the one assignment yet to put in there. And that should be done hopefully within the next half hour or so. I don't make